Hello, in this video we're going to talk a little bit about arithmetic sequences. We can take any class of continuous functions and restrict the domain to the set of natural numbers to obtain a corresponding class of sequences. The most basic and important class of functions are the linear functions. When we restrict the domain of a linear function to the natural numbers, instead of calling it a linear sequence, which would make sense, we call it an arithmetic sequence. We already know a great deal about linear functions, so this knowledge will transfer to arithmetic sequences. For example, we know that a linear function has a constant derivative and thus a constant slope. Recall that the slope is the amount a function goes up, if positive, or down, if negative, when the input is increased by 1. In other words, the slope is delta y when delta x is 1. For a sequence, the change in the input is always 1 when going from one term to the next. Delta k or delta x is always 1, at least if you're going from one term to the next. Therefore, we see that the slope or rate of change between successive terms is just the difference between those terms. So arithmetic sequences have a comma difference between any pair of terms. Because it's a comma difference, it's often called D. The comma difference is often called D when dealing with arithmetic sequences. I prefer to continue to use the letter M for the comma difference, the slope. Therefore, we see that arithmetic sequences have the following formulas for constant slope, comma difference of M, and a specified first term of a sub 1. Note that the common constant slope is the comma difference. The slope is a sub k minus 1, a sub k plus 1 minus a sub k for any natural number k. So I can give you both a recursive and an explicit formula for an arithmetic sequence in general. Of course, with the recursive formula, you first specify the first term. And then you have a recurrence relation that is a sub k equals a sub k minus 1 plus m being that slope or comma difference. And that works for k greater than 1. Some people would use a d there instead of an m. For an explicit formula for an arithmetic sequence, a sub k is m times k minus 1 plus a sub 1. You take the first term and you add k minus 1 m's to that. Okay. So we're adding m each time. K minus 1 tells how many times we add it. Now, if we work this out, that's mk plus a1 minus m. And that would be what the zeroth term would be if we would allow an input of 0. In fact, sometimes for sequences, we do allow an input of 0. So it's m sub k plus a sub 0. So a sub 0 is kind of a non-existent term the way we're defining it. So we define the 0th term as a sub 0, which is a sub 1 minus m, but it's technically not part of the sequence. Because we're letting the domain be the natural numbers 1, 2, 3. And of course, the graph will consist of collinear isolated dots. So let's write out the first 6 terms in recursive explicit formulas for an arithmetic sequence with common difference, with initial term 4 and common difference 5. So see if you can find the sequence yourself, both versions. Come back when you got it ready. Press pause now. Well, we start with 4, and we add 5, and that's 9. And we add 5 more, that's 14. We add 5 more, that's 19. Then 24, then 29, and so forth. So the recursive definition is a sub 1 is 4. A sub k is a sub k minus 1 plus 5 is your recurrent relation. And that's true for k greater than 1. Explicitly, a sub k is 5 times k minus 1 plus the first term of 4. Or, if you'd rather rewrite it as 5k minus 1, that's correct as well. And there's the graph of it. Of course, the points are isolated points in a straight line. Let's extend that idea. So the constant sequence has terms all the same. For example, 2, 2, 2, 2, 2, 2, 2. An arithmetic or linear sequence has a common difference. it's not a constant sequence, but the differences are the same. In other words, if we were to find successive differences, 8 minus 3 is 5, 13 minus 8 is 5, 18 minus 13 is 5, 23 minus 18 is 5, 28 minus 23 is 5, and so on, that's what we call the first differences, or the differences are common, they're constant. That makes it linear or arithmetic. So if we were to extend this to a linear function, then it would have a constant first derivative. Quadratic functions, second-degree polynomial functions, have a constant second derivative. So quadratic sequences will have a constant second difference, the difference of the differences. Cubic functions have a constant third derivative, so cubic sequences will have a constant third differences, and so on. So in general, an nth degree polynomial function has a constant nth derivative, so the nth degree sequence will have a constant nth difference. So here's an example. Find an explicit formula for the following quadratic sequence, 0, 0, 2, 6, 12, 20, and 30. Now I said it was quadratic. How can we tell it is? We could find the differences. So the terms there are written out, 0, 0, 2, 6, 12, 20, 30. The x's or inputs are n, or actually I usually prefer to use k. 1, 2, 3, 4, 5, 6, 7. The differences then would be, well, 0 minus 0 is 0. The next one, 2 minus 0 is the 2 here. 6 minus 2 is 4. 12 minus 6 is 6. 20 minus 12 is 8. 30 minus 20 is 10. Certainly it's not a constant function. And the differences are not constant, so it's not arithmetic either. But when we do the difference of the differences, 2 minus 0 is 2, 4 minus 2 is 2, 6 minus 4 is 2, and then we get 2's for the last two as well. The second differences, the difference of the differences, is actually constant. This indicates a quadratic sequence or second degree polynomial. Now, assuming this pattern continues forever, the sequence must be quadratic. Just as any 2 points with different first coordinates determine a unique line, any 3 distinct non-collinear points with different first coordinates determine a unique quadratic function. Choose any 3 points and substitute in the general form to get a system of 3 equations. Solve for the coefficients. So in other words, I'm going to take these first 3 points. If we get a quadratic function through those 3, it's going to automatically hit these other 2 because of the pattern we have. Other infinitely many points in the sequence. So we're taking the form ak squared plus bk plus c equals d sub k for this sequence. And we're going to plug in k as 1, and then we'll get d as 0. We'll plug in k as 2, we get d as 0. Plug in k as 3, we get d as 2. So this is 1's in here. And so when we work that out, that's 1a plus 1b plus 1c equals 0. This gives us 4a plus 2b plus c equals 0. And this gives us 9a plus 3b plus c equals 2. One way to do that is to put this in a matrix of coefficients. Coefficients here are 1, 1, 1. Then you got the equals and then 0. And that goes like this. So the next one would be 4, 2, 1, 0. And the next one would be 9, 3, 1, 2. Notice that these are all 1's because that's just, there's no k to plug in there. These are just 1, 2, 3 because it's just k. These are all k squared, so it's 1 squared, 2 squared, 3 squared. So these right here are powers of 1, powers of 2, powers of 3. And these right here are the terms, 0, 0, and 2. Now we do the technique called Gauss-Jordan matrix reduction on this, which is can be accomplished with a graphing calculator. And that produces a matrix on the right that's in reduced row echelon form with the same solutions. And this one says 1a equals 1, 1b equals -3, and 1c equals 2. So this is a, b, and c. And so that says d sub well, there it is in n's. Let me go ahead and switch it back to k's because we were using k's before. Of course, it's correct with either letter. So d sub k equals k squared minus 3k plus 2. This does factor as k minus 1 and k minus 2. You could also write it as k minus 3 halves squared minus 1/4. So this could be thought of as as a what might be called general form, or the 0th term would be 2 if we were allowed to extend back. And this is the factored form, and there's a sort of a vertex form if we were to extend this to a full all real numbers for k, then the vertex would be 3 halves comma negative 1/4. But I'm going to stay, I'd say just that first version is plenty good right there. Now that's an example that I pulled from my algebra notes. In calculus, we could have solved for a little bit more easily, or at least differently, by extending the domain to all real numbers. We have f of x equals ax squared plus bx plus c. F prime is 2ax plus b, and f double prime is 2a. So we know f double prime is that second difference of 2. So 2 equals 2a. That tells us a has to be 1, which agrees with what we had here. So we can do that, then put in what's left to get 2 equations and 2 unknowns to solve. Now, if you didn't follow what's going on here with this this technique of reducing this matrix and why that solves that equation and so forth, and how to do it on a calculator, then I encourage you to review some algebra. And one way to do that is to look at my algebra videos. I have in my algebra playlist, I have a section in the third playlist in algebra, video 3.12.3, systems of equations of linear type using matrices, where I'll go over that technique. And then 3.12.4 algebra video will have systems of equations of linear type via a calculator, and I'll show you how to get this in your calculator. Let's do another example. So once again, recall that 1 point determines a constant 0-degree polynomial function or horizontal line. 2 points with different first coordinates determine a linear or first-degree polynomial function. 3 non-collinear points with different first coordinates determine a quadratic or second-degree polynomial function. Similarly, we can extend this idea so that n plus 1 points determine an nth degree polynomial function, unless it degenerates to a lesser degree function. If we apply this idea to sequences, then we see that any listing of n plus 1 terms of a sequence could be represented exactly with an nth degree polynomial sequence. However, this is not the only sequence that would have those n terms. In fact, there's infinitely many sequences that will agree with any number of finite terms. So when they say, find a pattern here, well, there's lots of patterns that will work. In fact, we've already said that a polynomial pattern will always work. If a function has a common nth difference, okay, for let's see here, let me fix this. For all successive terms, then it is a polynomial sequence of degree n. It takes n plus 1 points of this sequence to be able to determine the formula for the function. Okay? The function specifically is a sequence, so let me just go ahead and say sequence. To do this, simply substitute the input-output pairs into the general form. It's going to look something like this, where the c sub whatevers are constants. Plug in 1, 2, 3, 4, 5 up to, however many you need, up to n plus 1 in place of the k's and the corresponding terms here. And that's going to give you a simultaneous set of n plus 1 linear equations. And we can always solve that for the unknown constants, for example, using matrix, because it's always going to be a linear type equation. Okay, so let's do another example. Fill in the blanks for the next two terms to derive a formula for the k term of the following and I've said polynomial sequence. So we're told the polynomial sequence. So it must have a common nth difference for some degree n. It's clearly not a constant sequence, so let's figure out the first differences. The first differences are 3, 7, 11, and 15. Well, that's not constant, so it's not arithmetic. Let's try again. The next differences are 4, 4, 4. Okay, those are constant, so we got us a quadratic sequence like the last example. Okay, so the next first differences must be, well, add 4 to this, that's 19. Then 19 plus 4 is 23. So then we add 19 to 40 to get 59, and take 59 and add the 23 to get 82. So those are the next two terms. So it must have a formula of this form right here. So take the first 3 points, right? 1, 4, 2, 7, and 3, 14, or any 3 points that you want, but I always like to use the first 3. They're usually the easiest ones to pull. And substitute into the equation to get a system of linear equations in A, B, and C. Create a matrix of coefficients converted to reduced row echelon form using the RREF command on your calculator to solve the system of equations. And you might check it by putting the formula you get into Y1 your calculator, set the table start at 1, go up by 1, and view the table to check your work. So here's the basic setup here. So notice the first part of this is the same as the last example, and these are our points here, 4, 7, and 14. Our calculator returned this when I did it on a calculator. So there's your A, B, and C. And so the formula is A sub k is 2k squared minus 3k plus 5. So if you always use the first terms, the first rows are powers of 1, 2, and 3. And the next row will be powers of 4 and 5 and 6 and so forth if we have more of them. Let's try another example. Fill in the blanks given the next 2 terms and determine a formula for the kth term of the following polynomial sequence. -4, 5, 32, 89, 188, 341, and 560. So I put this in Excel to get this here. So I just typed in my stuff here. For this one where it says this cell right here, I told it to take this cell minus this cell. And since I made it relative referencing, it was really easy. I just copied that and pasted it all the way across here, all the way across here, all of this, and then I pasted it here as well. And I kept doing this each line until I got a constant going across. Well, it happened on the third line, so the third differences are constant, therefore is a cubic. So I need to take the first 4 points and put them in a matrix, and I can solve for the coefficients. So the first line here, well, these are going to be the last column, -4, 5, 32, and 89 right here. First column is just all going to be ones, powers of 1. Next is going to be powers of 2. Reading from here to back to the left, it's 1, 2, 4, 8. 2 to the 0, to the first, to the second, to the third. Then I've got a 1 here, the powers of 3. 3 squared is 9, 9 squared is 27. 1, 4, multiplied by another 4 is 16, multiplied by another 4 is 64. Do RREF of that matrix, and we get this. This is actual output from a TI-84. And there's our A, B, C, and D. So our formula is 2x cubed minus 3x squared plus 4x minus 7. Actually, it should be k's instead of the x's. Instead of y1, it would be maybe a sub k. But I could do it with x's in my graphing calculator. If I set my table going up at ones, it produces the sequence right here. And there's the first terms. It does agree with what we've got as a check. Let's see, up to 560. Yeah, that's the first 7 terms it agrees, and I can scroll down and get the next few terms if I want. So there's the formula right there in the right form. We'll look at some geometric sequences in the next video.